Hi everyone! Now that we've come to the end of these videos, let's quickly recap what we've learned. First, we learned about the basics of error-correcting codes. We learned that a code is just a set of points in sigma to the n. And we saw that if a code has good distance, that is the minimum Hamming distance between any 2 points, and good rate, that is if there are lots of these red dots, then Alice and Bob can use it to communicate efficiently in the presence of noise. We also talked about linear codes, and we saw the concepts of generator matrices and parity check matrices, both of which were really useful when thinking about these codes and thinking about algorithms for manipulating them. We also talked about the fundamental trade-offs between rate and distance of a code. And we saw lots of bounds, like the Hamming bound, the Plotkin bound, and the Singleton bound, which were all impossibility results. And we saw some possibility results, like the GV bound and the Zyablov bound. Altogether, this told us a lot about the best trade-offs between the rate and distance for different codes. However, the question for binary codes, what is that best trade-off, is still open. For large alphabets, though, that is growing with the block length n, we do know codes that meet the optimal trade-off between rate and distance, and those codes are Reed-Solomon codes. Reed-Solomon codes are defined as vectors of evaluations of low-degree polynomials, and the reason that they have such a good trade-off between rate and distance is a fact that we have used repeatedly throughout this course.
Right! Low-degree polynomials don't have too many roots.
Yes, thank you, Polly. Also, we made a friend, Polly the polynomial interpolation parrot. Moreover, Reed-Solomon codes have efficient decoding algorithms. We saw the Berlekamp-Welch algorithm, and the reason that that algorithm worked was...
Right! Low-degree polynomials don't have too many roots.
Yes, thank you, Polly. We also saw several more codes that we could get, along with efficient algorithms, by building on or manipulating Reed-Solomon codes. For example, we saw BCH codes, which were just what happened when you took a Reed-Solomon code and restricted it to all of the binary code words. We saw Reed-Muller codes, which were sort of the multivariate extension of Reed-Solomon codes. We saw concatenated codes, which allowed us to take a code over a large alphabet, like a Reed-Solomon code, and concatenate it down to get a code over a smaller alphabet. The picture looked like this. That is, we start out with a Reed-Solomon code word, treat that as a bunch of bits, and then encode each chunk from that code word with some inner binary code to end up with a big binary code word. And we saw a couple of cool algorithms to decode such concatenated codes, both from random errors and from worst-case errors. We also saw folded Reed-Solomon codes, which turn Reed-Solomon codes into a code over an even larger alphabet, but that has better list decoding capabilities. Speaking of list decoding, another thing that we saw in this course was a whole bunch of other notions of decoding. For example, list decoding is the problem to find all code words close to the received word, even if there might be more than one of them. The picture looked something like this, so we wanted to return all of these code words. We saw a few algorithms for doing this, like the Guruswamy-Sudan algorithm, and the algorithm for list decoding folded Reed-Solomon codes, both of which worked because...
Right! Low-degree polynomials don't have too many roots.
Yeah, thanks, Polly. We also saw local decoding, in which Bob wants to find something about Alice's message in sublinear time, even in the presence of worst-case errors. That is, some adversary corrupts the code word in a bunch of places, and now Bob has to make queries to the code word to figure out whatever it is he wants to figure out. For example, maybe just one bit of Alice's message. So that was local decoding. We saw that the Hadamard code and Reed-Muller codes support local decoding. Then we combine these notions of local decoding and list decoding to get local list decoding. In local list decoding, we have the same picture as in local decoding, except that there are several Bobs because there might be multiple code words close to the received word. We saw an algorithm for local list decoding the Hadamard code. We also talked about a different version of locality called a regenerating code. In a regenerating code, just one symbol is missing. And Bob's job is to recover the missing symbol using as little downloaded information as possible from the rest of the code word. We saw that Reed-Solomon codes themselves are actually pretty awesome regenerating codes. Throughout these videos, we've also seen several applications of error-correcting codes. There's our original motivating application in communication, and another natural application in storage. Regenerating codes in particular were designed for distributed storage. But we also saw applications beyond communication and storage, like applications in cryptography. We talked about the Michaelis crypto system. We also mentioned some applications in compressed sensing. And we saw applications to streaming algorithms like the heavy hitters problem. In particular, we saw 2 ways to use Reed-Solomon codes to get faster algorithms for heavy hitters. We also saw applications in group testing. We saw how to use Reed-Solomon codes to get good group testing schemes. We saw applications in learning theory. That is, we saw how our algorithm for locally list decoding the Hadamard code gave us an algorithm for learning Fourier sparse Boolean functions from queries. Plus, there are tons of other applications we didn't have time to get to in these videos. So what's the moral of the story? One moral is that error-correcting codes show up all over the place. They're extremely useful in communication and storage, but they're just really useful combinatorial and algorithmic objects in general for lots and lots of applications. Another moral of the story that perhaps you might have picked up on is that
Right! Low-degree polynomials don't have too many roots.
Yes, thank you, Polly. Low-degree polynomials don't have too many roots, and this fact is stupidly useful in a wide variety of applications. There's probably a lot more takeaways I could list here, but let's leave it with these 2 for now. Okay, so thanks for watching these videos. I hope that you've enjoyed them and that you've learned something, and that you are inspired to either keep learning more about error-correcting codes or to use error-correcting codes in your own work, or ideally both.
Right!
Yeah, I think they get it, Polly.